All right. Well, thank you very much for the opportunity to visit Vienna. It's my first time here. It's lovely. Thanks to the organizers for giving me a chance to speak as well. As mentioned, I'll be giving a review talk about fractons. This appears to be Fracton Day as far as I can tell, so hopefully this will set the stage nicely for things to follow. What are fractons? We heard a bit about these things yesterday. These are hypothetical, this time purely hypothetical, no one has seen such things in nature yet, systems that largely come to us from condensed matter physics. They have an interesting history in their own right, largely in the context of glassiness and proposals for very long-lived stable qubits. But they have become interesting to an audience of high-energy theorists for a few reasons that should be clear by the end today. These things, they're sort of generalizations of symmetry-protected topological phases. And their most visceral feature is, well, the existence of these things called fractons, which is a bad name. But what does this mean in practice? These refer to finite energy, but immobile quasi-particle excitations of these systems. You make a fracton and it's stuck. It can't move. They have fusion rules. You make two of these things, then they can bind together into something called a linon, and quasi-particle excitation of finite energy that can move along the line. And you can fuse linons together to planons that can move along the plane freely, and you can fuse those to make something that's completely mobile.
Right, but being deaf, I don't know what CMT is.
Oh, sorry, I said condensed matter theory? Condensed matter theory? Symmetry protected topological. Yeah. And of course, don't hesitate to ask if there's any questions along the way. Yes. Yes. That's right. That's right. So for instance, we have SPT phases. People have found time reversal invariant topological insulators in various media, but these not so much. It's a work in progress. Now, the reason why these things have become of interest in our community in high energy physics is that they challenge long-standing beliefs about the universality and effectiveness of renormalization group. That is to say, they challenge the whole effective field theory paradigm of Wilson. The usual paradigm is, we given some complicated microscopic system, if we look at it over long scales, well, all the details microscopically don't matter. There are some relevant degrees of freedom, relevant symmetries. And we can write down effective descriptions consistent with those symmetries for those degrees of freedom, and all of the microscopic details get absorbed into irrelevant operators, and so on and so forth. Roughly speaking, that physics is organized according to energy scales. And in these, this idea, of course, has been enormously fruitful. It works, of course, in condensed matter physics. It also works in our field. We talk about, Calabi-Yau compactifications of string theory, where we have an effective field theory description at long distance. We talk about lattice QCD. We talk about spin chains, basically whatever you want. This paradigm works very well. This is not true in these funny systems called fractons. Yeah, this is where, exactly. So what's the thing that makes RG and effective field theory cook? It's that physics is organized according to scale, that high energies decouple from low energies. That is precisely the thing that is not true in these systems. As we will see in some detail. Okay, so rather than giving some song and dance about motivation for why people started writing down these models, let me just kind of get into it. Let me write down some theories of this sort that at first glance look innocuous, but as we'll see, well, they have these funny features. So to start with, though, the systems I'm going to write down don't have fractons per se, as will be clear that you should really think of them as systems with some exotic symmetry. Exotic will be something that will be clear from the context, will be defined shortly. I don't have a crisp definition for it. To be defined. So here's an example. This is due to Seiberg and Schau. Consider a Lagrangian for a field chi, which has Lagrangian a by 2 for a some parameter, chi dot squared, minus another constant by 2, partial x, partial y, chi squared in 2 plus 1. With chi, an angular variable. Circle valued. This would prohibit a potential. You could have cosine potential and so on, I suppose. But you have an ordinary time derivative term, and there's this funny spatial kinetic term that's 4 derivatives rather than the usual 2 derivatives. This theory has an exotic symmetry, something that we're not used to. It's called subsystem symmetry. In particular, it's invariant under chi goes to chi plus some function of x. Let me just write down the transformation. Plus some function of y. Yeah. That's right. These are non-relativistic systems. Yeah, that's right. These are completely independent. Maybe calling them f of x. Let me, just to remove any possible thinking that they're completely different functions, and also arbitrary functions. Arbitrary function of x, arbitrary function of y. You might think for a moment that these are gauge symmetries. There are some arbitrary functions. These are not. These are global symmetries. They're time independent. Yeah. This is also true. Right, so this is a very funny system indeed. You might ask where such a thing could come from, since chi is shifting under a symmetry and it's a phase variable. It's natural to wonder if this comes from some sort of symmetry breaking phenomenon, that chi is a Goldstone boson for some more microscopic description. And indeed, you can write something down as a candidate that would do the job. This, you know what's the better eraser here? It's this. This, really? This right here? You did. I should have figured this out before.
This technology.
Okay, yeah.
This one?
Yeah, this one right here. And then you have to, Daniel, you're a professional. Watch carefully. Okay. Fantastic. Okay, so good. So you know, at least you can write something down that let's call it L prime that this might come from. Let's suppose that we have a field chi, complex field, which has some modulus, and then where chi is its phase, circle valued. We can write down a candidate Lagrangian, phi bar with an I, single time derivative, minus I mu, phi, minus g by 2, something. Let me, partial x, phi, partial y, phi minus, partial x, partial y, phi, with another phi there, complex square, and then minus, say, some quartic coupling. I don't need a parenthesis because I'm writing a Lagrangian, not an action. So this is something that, you know, has an effective potential, which has a quartic term and a quadratic term. And you can imagine then that if I take this parameter, which in this context, this Lagrangian describes a many-body quantum mechanics. It's a non-relativistic effective field theory, has a single time derivative. You would identify the parameter sitting in here as the chemical potential. So you crank up the potential to be large and positive. You're dealing with standard Mexican hat. This looks abelian Higgs-ish. And you might think that you drive some symmetry breaking, sit at the minimum of the potential, and then that there should be a effective description of the phase field chi. This action, so constructed, is invariant under phi goes to e to the I f of x plus g of y times phi, in which case your phase would inherit that symmetry. It would shift under this transformation. So this is an instance of what I mean by exotic symmetry. It's a very funny thing indeed. And yes? Let's see. So my approach so far, I'm writing down a continuum Lagrangian first, and then what we'll do is we'll connect this over the next bit of time to a lattice model with spins, and then we'll see in what sense this corresponds to something that a condensed matter theorist would call a subsystem symmetry. Yes? Yeah. Hold on. Yeah. That's why I'm saying this looks innocuous at first glance. This looks consistent with the paradigm. Setting up the stage, so. Yeah. Okay. Another thing that we could write down that doesn't have subsystem symmetry, but has something that you could call a dipole symmetry. It's kind of related. We can call example 2. Again, for a phase field chi, time derivative term, and then a kinetic term that instead of the usual grad chi squared, a kinetic term that has grad squared chi squared. So 4 derivatives. This has the virtue at least of being rotationally invariant, unlike that, but on the other hand, it's the spatial derivatives are softened compared to the usual thing. And this model is invariant under another funny symmetry. We can shift chi by a constant, derivatively coupled, but we can also shift it by a function that's linear in x. Oh, let me. Okay, sorry for that. And let's see. So this would correspond to an ordinary non-linearly realized U1 symmetry, and this to a nonlinear realized dipole symmetry, whose corresponding conserved quantity would be the dipole moment. And again, we can write down something a little bit more microscopic in terms of a phase field phi, which we might think flows to this at long distance. In this case, something like this, which again has a potential effective of Mexican hat type. Did I? Oh, so complex square. Here. Oh, yes, thank you. Thank you. Yes, let's write correct expressions that don't vanish. Right, so again, you could, at least classically, look at minimum of the potential. Extremize, look at fluctuations around the minimum. They behave like some phase field with an effective Lagrangian of this type. This system is invariant under a linearly realized version of this funny symmetry from which the phase field would inherit a shift version of the same. This sort of thing has a long name, sometimes is called Lifshitz theory. It has a scaling symmetry whereby time scales twice as much as space. Sometimes you call it z equals 2 for that reason. But in the context of careful path integral treatment, like the type I'm discussing today, this was considered recently, again, by Garantla, Hotot Lam, Seiberg, and Shao. And these sort of models that I'm writing down here that at least seem like they could float to these at long distance, these sort of models were written down by Pretko some years ago. As I mentioned, these Lagrangians, they look relatively innocuous. They seem consistent with effective field theory paradigm, but actually both of them display rather strange phenomena, as we'll uncover. I'm going to focus on this example with subsystem symmetry, just for lack of time. We can do the other one in offline, if you, just for lack of time. In particular, these systems display the aforementioned UV IR mixing, despite looking perfectly fine. And the other thing that they have, well, is a density of states that depends on the details of an underlying lattice that the thing lives on. In other words, it depends on the UV. To see the UV-IR mixing, a classical treatment is not really sufficient. We have to carefully investigate the behavior of these theories quantum mechanically. You have to quantize them. You have to perform path integral or canonical quantization or what have you to really see the problems. That's right. You'll have something omega squared going like k to the 4, for instance, in this setting. Or in this one, omega squared going like kx squared, ky squared. So the, well, hold on. Let me, yes. Yes. Well, so in this case, I'm writing down a version of this quartic interaction, similar type over there, that is rotationally invariant, and that is only invariant under this transformation. This one is not rotationally invariant, and I've picked the combination that's invariant under this. Yeah. Well, right. So these Lagrangians I'm writing down here, these more microscopic things, we'll have more to say about them later. Since we're on the point now, can comment a little bit on these. These are funny beasts as well. I have a time derivative term. In this case, dipole symmetry forbids the usual spatial kinetic term by symmetry. And so the leading terms with spatial derivatives are quartic in, well, in this case, quartic in derivatives and quartic in fields. There are some other terms that I can write down that are a little bit simpler that are second derivative, but quartic in fields. They're non-Gaussian, and it's far from clear, how to make sense of such a theory quantum mechanically.
Because there are no time derivatives.
Yeah. That's right. We don't have to. Yeah, this is also true. Yeah, one-time derivative, you don't have to worry about ghosts, but quantum mechanically, this is non-Gaussian. Okay, other questions before moving on?
Well, maybe a general one. Other group of people that study.
Yeah.
Is there any relation between?
No, it's different. Yeah. There's no mixing in that context, to my knowledge. Okay, so what I want to do in...
Could you comment like ax to 0, ay could be anything.
That's right.
It is legal to say that I see
Well, so good. So indeed, you're anticipating nicely where this is going. So quantum mechanically, the modes with either kx is equal to 0 or ky is equal to 0 are 0 modes, and we have to treat those very carefully. In the context with subsystem symmetry, those will lead to UVIR mixing. There's a classical precursor to the problem. But the problem that we'll find quantum mechanically is that if we introduce a lattice regulator, that the thermodynamic limit and the continuum limit do not commute. That's something that you really need to treat at the quantum level to see. In the case with dipole symmetry, it's less severe. You would say the modes that are, the 0 modes are just those with k is equal to 0. It's true even for an ordinary relativistic massless system. But here they will present, and I wasn't going to talk about this in detail just for lack of time, but they also present an obstruction with respect to mixing. Okay, so plan for the rest of the talk. And now this is where you get to come up. See if you can. Although I shouldn't laugh because I'm chairing the afternoon session, so I have to. So let's do this one right here, yeah.
reminds me Maslow at a conference. He was sitting and directing people to use that. Are you Maslow?
Secretly, yeah. And let the whole.
No, when you come back.
No, I was not faster. That's a lie.
Okay. Thank you. Okay, so we've given some kind of introduction. What I want to do from here is to give a careful quantum mechanical treatment of this first example. And next, I'll talk about how, these models that I'm writing down of chi's, they don't have fractons. They have exotic symmetry, but not fractons. We're going to get fractons by coupling to something called tensor gauge theory. And then I'll discuss in the last part more mesoscopic description, where these symmetries are linearly realized rather than nonlinearly realized, which I'm going to tackle by considering large N generalizations thereof. That's the plan. Let's go back to this Lagrangian of example 1. That guy, and 2 plus 1. Let's quantize this theory together. How do we do it? So, natural thing to do is to go to Fourier space, since position doesn't appear explicitly in this Lagrangian. And, well, at least for non-zero kx and ky, we're dealing with an ordinary quantum mechanical system, quadratic, just a harmonic oscillator. Sure. There's a canonical momentum. And then the spatial derivatives give a potential as such, with chi canonically conjugate to pi in the usual way. And so you get some oscillator with energies, well, with the usual energies. This is not where the interest comes. The interest comes in the treatment of the modes with either kx is equal to 0 or ky is equal to 0. Perfect timing. Well, for these, it's convenient to reorganize the problem not in the Fourier basis, but in the position basis, or to consider modes that are independent of y and independent of x, which I'll call chi1 and chi2. So in other words, you can think of decomposing chi into a sum over momenta not 0 and chi1 and chi2, provided that we also account for the fact that, well, the 0 mode of chi1 and the 0 mode of chi2 are not independent from each other. I can perform this decomposition at the expense of introducing a redundancy under chi1 of x goes to chi1 of x plus some constant, and chi2 of x goes to, or chi2 of y goes to chi2 of y minus the same constant. And I've introduced no extra degrees of freedom. Although this is a very, very minor perturbation here. Right, so let's look at these modes chi1 and chi2, they decouple from each other. Let's look at the action just for chi1 for a second. So the action for chi1, well, it's independent of y. Leads to an overall factor of the size of the y direction in the action. So let's consider now changing the problem from the usual one that we might think of in infinite volume to one on a torus. Of sides Lx and Ly. In which case the action for chi1 is Ly integral dt integral dx alpha by 2 chi1 dot squared. Okay, if we're working in the action formalism. And well, now nothing here depends on x. One way of kind of tackling that is to not just consider the problem on a torus, but on a toroidal lattice. We work with a lattice approximation, in other words, to this system, where the lattice spacing, let's call it A. In which case, in our lattice-regulated version of this theory, we have Ly times A, sum over lattice sites in the x direction. I'll call that sum over I, integral dt, alpha by 2, chi1 at site I, dot squared. So chi1i is chi1 at lattice site I. And if you construct a corresponding Hamiltonian for this mode, well, this free factor here appears in the denominator. That's the effective mass of this mode. So the Hamiltonian now is a sum over I corresponding momentum squared over 2 alpha Ly A. So it's pure kinetic energy, but with an effective mass, it's very unusual. The size of the y direction times the lattice spacing. Now, because chi is a phase field, these momenta are integral. As a result, the spectrum of these modes is just integer squared over this. That right there, though, is precisely the UV-IR mixing I was talking about earlier. How do we see that? So the spectrum, is some integer squared over 2 alpha Lya. It's this guy that gives us interesting physics here. There's two natural limits that we could consider in this problem. One is the continuum limit. This is the usual one where the lattice goes away. That's where A tends to 0. And in that limit, well, all of these states with non-zero Q, non-zero excitation number, their energies become lattice scale, of order 1 over A. So those states are sent off to the sky. On the other hand, we could take the thermodynamic limit. Ly tends to infinity at fixed lattice spacing. So your lattice just becomes very, 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 very big. And in that case, all of these states have energies that are parametrically small. They become very light. And clearly, which limit we take, those two limits are distinct. They're very different from each other, and the limits do not commute. This is not the usual thing. In case you've never done, I know for many of you probably, I don't know how many of you have looked at lattice quantum field theories before. This is the opposite of what usually happens. Usually the thermodynamic and continuum limits commute. So what we end up getting in this case, if we think about the continuum theory, so where we take A to 0 first, is we get a UV sensitive spectrum. And in particular, all the states that the states with these Qs, those are the ones that are actually charged under this subsystem symmetry that we mentioned before. This is a peculiar instance in which, in the continuum limit, all the states that are charged under this funny symmetry have lattice scale energies, and therefore at low energies, there is no charged states left. This has the implication that in this, even though we have a theory of a phase field, that the underlying symmetry here, this subsystem symmetry, does not actually undergo spontaneous symmetry breaking. It's more analogous here. There's a very, very loose parallel with the treatment of compact bosons in 1+1, where you also can't have symmetry breaking, even though you can have a theory, a sigma model, something that looks like it arises from symmetry breaking. Except here, the states that carry charges are off in the sky. What else? Another feature then that we get of this phase is that this phase is really gapless. Doesn't look at all like the physics of fractons. The states that, got erased. But there are these states that carry energies of order kx, ky. And therefore, for arbitrarily low wavelength, along wavelength, you get arbitrarily low energy. So there's arbitrarily low energy excitations. We're dealing with a gapless phase. Okay, so we've seen the UV-IR mixing from these innocuous theories. We've seen that we can make sense of it by careful quantum mechanical treatment. So we're not just completely screwed. But one could ask, given the title of the talk, what about the fractons? Yeah. Sure, you could, well, so something that you could do, for instance, would be to tune alpha to be of order 1 over the length, or 1 over a. Usually, we don't adjust couplings to scale with geometry or with the lattice. So you can do that to kind of take care of these, but then you introduce other problems. I mean, in particular, the spectrum of modes with non-zero momentum, you're going to screw that up. Yeah. No, it's not. So L here is the physical size. It's the number of lattice sites times A. I mean, you can imagine taking other limits, but these limits are... Oh, sorry. No. The length is the physical. So usual thing in lattice is that you have, say, n sites with lattice spacing A, and then the length is n times A. So this right here, this is the number of lattice sites in the y direction, A squared. Right. That's right. Yeah. We have this other part of the spectrum. The usual scaling is you send, how to say, so the usual thing familiar in lattice quantum field theory is you send A to 0 while keeping the physical geometry fixed. But you usually have to scale the couplings as you do that in order to achieve a finite continuum limit. In this setting, you can choose those couplings to make this sector perfectly normal, but at the cost of killing the sectors with non-zero momentum. Well, the spectrum, again, or the Hamiltonian that you would get for those modes of non-zero k, is this. And the limits where you would kind of fix this up are where you scale alpha to 10 to 0 with either the thermodynamic or the continuum limits. Or you make it go like 1 over L or 1 over A. But then you're doing something quite violent here. You're either killing or sending the kinetic energy of these modes to infinity. Yeah.
That's your case, okay.
You right. Well, yeah. That's right. One way of saying it in the path integral language is that if you carefully, you perform integral e to the is in this case, then there's zero modes and winding modes that you have to treat. And those zero modes, you get IR divergences in field space corresponding to those, which if you resolve in terms of a sum over states, say thermal partition function, you run into this same issue. I'm presenting it in the language of canonical quantization, but there's a completely equivalent path integral treatment of the problem. Okay. That's right. Yeah. That's another, like the thing that I wrote down initially looks like a continuum Lagrangian, but it's afflicted with these divergences that I treat using a lattice regulator. And the lattice theory is unambiguous, but it lacks a conventional continuum limit. Hopefully the relevance, it should be clear that this may be relevant for the people doing Carroll in this workshop. You write down a classical Lagrangian that has funny properties and yeah. Go ahead, Dima. Sorry, say that one more time. Partition function? I mean, partition function, it's just usual trace c to the minus beta h in this case. So if you consider the partition function with a spatial lattice and then integrate over time, then it's what you would get from summing over states with these energies as well as these. How does it depend on A? I mean, through these energies. Yeah, just the usual way. Mm-hmm.
Features have been discussed in
Mm-hmm.
One you get, but you include both.
Mm-hmm.
Include both this
Mm-hmm.
So is that
well here I'm not making any connections with.
I'm not saying you're making a connection.
Yeah.
The similar feature.
Mm-hmm. It resembles work in. Mm-hmm. Mm-hmm.
The point of the continuum description is that the continuum both degrees of freedom.
Yes.
Not just
That's where I'm going with, I write down, if you will, the continuum Lagrangian I started from is a naive first step. It's not the real thing. Right. So, and this is, right. So you can talk about, so you may recall I wrote down these theories before with Portic, blah, 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 that you might think flow to these at long distance. I will have more to say about those Portic theories. Those are interacting theories. And you get all the same, you get the same physics. Okay, so where are the fractons? This is where coupling to tensor gauge theory comes in. What is tensor gauge theory? This is analog of electromagnetism in this setting, which has A0 and another guy with two indices, AXY. With a gauge redundancy, A0 to A0 plus lambda dot, and AXY to AXY plus partial X, partial Y lambda for any function lambda. together with, in the context of chi to chi minus lambda q, where this is some, maybe I shouldn't call it q, call it, okay, q with maybe a thing on the bottom to distinguish it from the q over there, but an effective charge for a field chi. Out of this, I can form an analog of electric field that is gauge invariant. And you can write down something like a Maxwell action for that. But in this context, what I want to do is I want to couple this tensor gauge theory to this gapless phase with this effective description in terms of chi. In other words, well, I can do that. In this way, and the most minimal coupling is just to replace chi dot with chi dot plus a naught, and partial x partial y chi plus a term with a. This is simplest gauge invariant action I can write down consistent with symmetries of the problem. One could imagine, for instance, adding a coupling, adding an e squared. Thing is, you stare at this for a moment, and you realize that what is chi doing is it's Higgsing the tensor gauge theory, effectively giving a mass to the tensor gauge field. And we could go to something like a gauge chi 0 locally. In which case, this acts like a mass term for the tensor gauge field in the usual sort of way. And what we end up with then is a massive phase, not a gapless one. And in this massive phase, one might think that there's a trivial vacuum. But actually, if this charge here is not 1, you end up with a TQFT-like description at low energies, as a BF-like description. And this will connect us to, for q bigger than 1. I know I've been working in 2 plus 1 to make life easy. Let me consider a 3 plus 1 dimensional version of the problem. Which has some connection with the condensed matter literature. And go through a version of what I said now in 3 plus 1. And coupled to tensor gauge theory, blah, 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 you end up with a TQFT-like description. It's a BF kind of theory. And at least if Q is equal to 2, that TQFT has a non-trivial ground state degeneracy on the torus. You can think of it as just counting like inequivalent Wilson lines around the cycles. Now, ground state degeneracy, unlike in the context of Chern-Simons theory or fractional Hall effect, is not just some integer independent of the details of space. It depends actually on the number of lattice sites in each direction. For a large lattice, it goes like 4 to the number of lattice sites in the x direction, plus the number of sites in the y direction, plus the number of sites in the z direction. And it turns out that there is a lattice model which has the same ground state degeneracy, and in fact, for which this BF theory is the low energy description. That lattice model is sometimes called X cube. It appeared in Alexander's talk yesterday, originally written down by BJ, Ha, and Fu. This is a lattice model that lives on a hypercubic lattice. Get different color. Where the degrees of freedom are spin 1/2. So at each site, there's a spin 1/2 degree of freedom. And the Hamiltonian of this system, it's a sum of commuting projectors. And therefore exactly soluble. And what it has is a subsystem symmetry. In which, if you take all of the sigmas on a given plane, we're used to spin systems where you can like flip spin in a direction for all the spins on the lattice, and that's the symmetry of the problem. That's the Z2 symmetry. Well, in this case, there's a much bigger symmetry. You can take all the spins on the given plane, a fixed plane of the lattice, fixed x, fixed y, fixed z, and roughly speaking, flip all of those spins. In practice, you can't flip sigma vector without screwing up the usual commutation relations, but you can flip 2 of the components and pick those to be x and y. And I can do that independently for each plane on the lattice. There's a Z2 for each plane. In fact, well, this Hamiltonian, it turns out, has an extra so-called magnetic subsystem symmetry, which is also Z2. And way of thinking about this non-trivial ground state degeneracy is that, well, if you write down a single ground state of this model, it's not invariant under these transformations. And so if you act with these symmetries, you fill out a whole multiplet. And because the symmetry has many, many Z2s, basically 2 for every plane of the lattice, well, that's how you get this. Z2 times Z2 gives you 4, the number of planes of the lattice. And connection with the TQFT, when if I Higgs a U1 gauge theory down with a charge Q field, you're Higgsing U1 to ZQ, in this case, Z2. So the thing that I was writing down earlier, this funny symmetry under chi to chi plus f of x, g of y, that's becoming this subsystem in the infrared after coupling to tensor gauge theory. Yes. You're probably right. Right? Yes, you're right. Thank you. Yes, they live on links. An easy fix. Right, so, and then what are the fractons? Well, this is a massive phase, similar to what happens in Chern-Simons theory, where the anyons can be represented in terms of Wilson lines. We can represent the fractons in the low energy description of this model in terms of Wilson lines, where you integrate A naught, but then the curve along which you integrate A naught by gauge invariance, since there's no AX and no AY, has to be just a line that goes straight up in time. In other words, it's just A naught dt. So the immobility of those excitations is encoded by the fact that the Wilson line that represents them can't move and can't acquire some velocity if you interpret it as a moving particle. Those are the fractons. Okay, so we've seen UV-IR mixing from careful quantum mechanical treatment. Now we see fractons by coupling to tensor gauge theory. The last thing I wanted to talk about was a more microscopic or more mesoscopic perspective on these models. Where do they come from? Which also addresses the question of whether or not interactions destroy all the things that I was talking about. So, you know, these theories of chi that we've written down so far, these are sigma models. They suggest that they come from some symmetry breaking. So they seem to describe quote unquote broken phases. I have to put scare quotes around the broken because we saw that in this careful treatment of this chi theory that the subsystem symmetry was not actually spontaneously broken, even though there's a phase field. With U1 global symmetry. But we should ask, can we write down interacting models that flow to these at long distance? Do radiative corrections spoil those flows? Are there other phases? We should ask all of those questions. And the simple quadratic theories of chi's are not smart enough, obviously, to answer those more granular, more microscopic questions. At least in this theory of chi that I discussed, coupling to tensor gauge theory, there was some microscopic model that we could match to, this x cube, but that thing was very special. It's the commuting projector Hamiltonian. It's integrable in some sense. And so one might wonder how much of this story survives for general interacting systems with these symmetries. Well, to answer that question, we have to start tackling these non-Gaussian Lagrangians that I was writing down earlier. Things like this. and trying to make sense of these as honest-to-God quantum theories. That, of course, is not easy because they're not Gaussian. And if you think for a little bit about strategies, how could we start tackling these, there's really not a lot to go with. So one strategy would be to say, well, let's take, that this thing has an effective potential, which has a quartic term, has a quadratic term. We can imagine tuning the chemical potential to be large and positive and try to trigger the symmetry breaking. We have Mexican hat, expand around minimum. And sort of hope for the best. Treat all the non-Gaussian parts, yeah, we'll probably need that. Treat all the non-Gaussian parts as perturbatively small and do a bit of this. We could do that. However, away from this regime, say if that chemical potential is negative, in which case our effective potential has a single classical minimum, and we just have no idea really what to do then. The Gaussian approximation to this theory lacks any dependence on spatial derivatives, and therefore it's, how do you make sense of loop integrals in that context? You integrate ddk of something that's independent of k, or perhaps polynomial in k, coming from the interaction vertices. What do you do? Well, there's another approach to this problem, which is to say, look, let me change, in the time-honored tradition of changing the question until we can answer it, let's, instead of having a theory of phi, a single phi, let's consider a theory of n component fields. Where n we take to be very, very large. And then I introduce factors of n so as to have a smooth n to infinity limit. So here I'll keep the parameters g and lambda 4 fixed while I send n to infinity. And in that case, I'm dealing with a glorified vector model, albeit not one of the type from the 70s, because the quartic terms, well, I have a conventional quartic term, but I have another one here that involves derivatives. Because we're at large n, on very general grounds, the system is weakly coupled in some variables. What are the right variables? Well, it turns out that the right ones are bilocal degrees of freedom. So I write down phi bar phi, and I sum over these like flavor indices. If I were to take expectation value of that, I'm dealing with the propagator for phi. Why I call it G. And well, this collective degree of freedom, this bilocal thing, if I rewrite my original theory of phi in terms of that, I need to introduce an extra degree of freedom, a Lagrange multiplier, that enforces this definition. There's another bilocal field that you integrate in sigma 1, 2. And well, yeah, just given the time, I can explain offline how this works. It's the same kind of engine that allows us to solve Chern-Simons matter theories, as well as the SYK. model. We can also glorified vector models. We can rewrite this original theory of phi in terms of a theory of G and sigma, so-called G sigma formulation. And in that formulation, 1 over n is the effective coupling constant of that model. Makes it clear then that at very large n, that those collective fields are weakly coupled. So, perfect, yeah, I'll work here. Thank you, Mark. So, solving these systems to leading order in large n amounts to solving the classical equations of motion of this collective model for the large n Green's function and this Lagrange multiplier sigma, which we call it sigma because it ends up having the form of self-energy. Those classical equations of motion, what do they look like? Well, in the I have to say a little bit first. So we ansatz. Oh, and I forgot to say this whole discussion of large n. This is due to myself and Amir Raz. So what you can do is you can ansatz that the large n saddle preserves translation invariance. In which case, this expectation value of Green's function is just a function of the separation. You know, because it involves a sum over n terms. It's also natural to ansatz that it's n times something. Whereas this guy, you would ansatz that it's a function of x1, 2 with no factor of n. And then in the Fourier domain, those large n equations of motion are g of omega k is equal to 1 over I omega plus sigma of omega k. Here I'm in, I've changed from Lorentzian, from real time to Euclidean signature. And the self-energy, there's another equation that says that this is minus the chemical potential plus 2 times an integral over something that looks like a loop momentum. A quartic interaction depends on the momentum omega k as well as the loop momentum g of q prime. And I'm using q prime to collectively denote a frequency and a momentum. And this quartic interaction, this comes from the underlying Lagrangian. This is like lambda 4 by 4 factorial, or sorry, by 4 plus g times, well, in this case, kx minus qx prime squared, ky minus qy prime squared. The simpler way of thinking about this is that one of these equations, the one for G, says that this field sigma takes the form of a self-energy in the large n Green's function. And the other equation is easiest to interpret diagrammatically. It amounts to saying that the self-energy is equal to an amputated diagram that's just a bubble where the large n Green's function runs around the bubble, and we have a quartic vertex here, and we amputate some external legs running into it. And then there's a momentum q flowing through this, and a momentum q prime going around the loop. Yeah. Just like in SYK, Chern-Simons matter. I mean, you could also treat the old literature on vector models in the 70s using this instead of Hubbard-Stratanovich. This is kind of some more general notion of Hubbard-Stratanovich that allows you to decouple any quartic interaction, even ones with derivatives. Right, so solving the model amounts to solving these equations. This can be done. Whenever you have integral equations, you need a little bit of help, but in this case, it's not so bad. And net result from solution is that we are able to uncover a phase diagram of these models. We're basically able to uncover the leading large N propagator and understand what symmetries are preserved, what symmetries are broken in the different phases. And what we find is 3 possible phases in these models. Let me plot things as a function of chemical potential and temperature. So we find one phase if our number of spatial dimensions, I'm going to say here, is bigger than 2. Here I was writing things in 2 plus 1, but let me just, for the purpose of summarizing result, let me first talk about more than 2 plus 1. We find a phase, roughly speaking, down here at positive chemical potential, finite temperature, but not too high, where the Green's function is 1 over I omega plus, and then some constant, k to the 4, plus some other constant, k squared. And I neglected to write it over there, but there's also a delta function piece indicating the existence of a condensate. In this phase, we have, this is the thing that has the sigma model description at low energies. When we wrote down this n component version of the model, I neglected to say this, we had to say what happened to the global symmetries. I wrote implicitly was talking about a UN invariant version of the theory instead of a U1 invariant version. And in this phase, UN is broken to UN minus 1. And the subsystem symmetry well, it sort of is spontaneously broken in the sense that there's a sigma model description at low energies, but it's not actually broken for the same reasons discussed before. The states that carry subsystem charges in the continuum limit are lattice scale. This is the analog over here of this, this theory of, at low energies, of this theory of chi that I wrote down earlier. There's 2 other phases, though. Next one is kind of up here where this temperature, this Tc, is of order 1 over the lattice spacing. And where this kind of spacing down here is of order the lattice spacing. So in other words, if I work just in a continuum regime, I only see 2 phases. But if I implement a lattice regulator, I see 3. And then there's some kind of smooth crossover over here between this phase with UN breaking and this other one. What are these other 2 phases? Well, in this phase, UN is preserved. But my large N Green's function looks like I omega plus alpha k to the 4, beta k squared, plus a constant. Negative, mu.
This is mu, sorry.
Sorry, yeah. This is the regime where the effective potential looks like this, and over here where it's like this. Yeah. Right, so you have this phase, and then I'll say more about this in a moment. What is this phase up here? This is one where the Green's function is 1 over I omega plus a constant. No momentum dependence whatsoever. We classify phases according to symmetry, a la Landau. What symmetries are preserved and broken in these phases? Well, it turns out that because the Green's function acquires a momentum dependence in this phase, that this subsystem symmetry is spontaneous, well, up to a U1 subgroup of it, this subsystem mod U1 is spontaneously broken in this regime. If you will, the one way of saying it is that this large N Green's function serves as an order parameter for this funny subsystem symmetry. When the Green's function has momentum dependence, that's a signal to us that that symmetry is broken. Spontaneous breaking of that indicates that there should be a sigma model description at low energies, analogous to this theory of chi. In this case, we can ansatz what, based on the symmetry breaking pattern, what the low energy description is, and it's in terms of a vector Goldstone rather than a scalar Goldstone. Up here, the phase that we find at lattice scale temperatures, that one is one where there's no momentum dependence in the large N Green's function whatsoever. That's a phase that where the subsystem symmetry is exactly preserved. Yeah, if you take the continuum limit, it's at infinite temperature, or at temperatures of order, tending to 0, but along the negative real axis of chemical potential. In non-relativistic settings, when you have a chemical potential, if you have negative chemical potential, you're dealing with a theory of nothing. Although in this case, it's something. So right, so this transition up here is first order. This one, it turns out, is second order up to some TC, and then it becomes first order. And you can see all of this from numerical solutions of these Dyson equations, wherever they were. Right, so other comment is that, well, okay, so to summarize maybe some features here, in general, this is a very broad lesson from this kind of analysis. You get gapless phases at low energies. Here and here. You really have to go to extreme lattice scale temperatures to find gapped phases. In particular, these exotic symmetries if I can anthropomorphize for a moment, they kind of want to be spontaneously broken, or at least to lead to sigma model descriptions. Even though the models that we were starting from were rather non-Gaussian, there are derivatively coupled sigma model descriptions at low energies. So there's approximately Gaussian descriptions in the IR. We also saw that interactions at higher energies didn't spoil this picture. The last comment, though, I want to make is that here I'm talking about a single solution. There's actually many solutions to these large N equations once you find a single one. There's a whole manifold of them swept out by this subsystem symmetry. And the number of such solutions is sensitive to the details of an underlying lattice. So in other words, even in this setting where we have large n and where we have these equations and we can solve them and it seems fine, there still is UVIR mixing, but it hits us in this kind of, again, sort of a funny, innocuous way. It, here, just through the number, sort of like a size of the vacuum manifold. We have about 0 modes associated with our solution, and the space of 0 modes is itself sensitive to the details of the lattice. Right, so I think we're basically at time here. Things went, yeah, so I think, yeah, probably it's just best to end here. Thank you very much for your attention.